Hello, and welcome to the second video in my R Newbie Diary. Today, we'll talk about relatively easy introductory topic in our language, operator syntax. By referring to operators, I mean non-alphanumeric operator symbols, or symbols which are not constructed with letters and numbers, things like plus, minus, less than sign, and alike. Many of the things which I'll cover may be familiar to you from your math classes, use of calculators, and interactions with other computer programs. But some of the operators have special meaning in our language, and good knowledge of their syntax is an essential part of learning to understand and use a new language. Our plan is outlined on this slide, so you can navigate right to the parts most interesting to you. You won't, however, learn how to make pictures as you see here, but there are probably some other good places on the web where you can learn this skill. So let's jump right into the first topic. Assignment of values. You won't get far in R without using this operator. As our documentation will tell you, it allows to assign a value to a name. And in R, you can actually assign name to almost any object, things like numeric, character, or logical values, but also data structures, functions, graphs, and many more things you will learn about when using R. As you see on this cover slide, there is more than one way to assign name to an object, and sometimes they are equivalent, but sometimes there is a difference between them, and you should make sure you know why you're using certain type. The first and the most common assignment operator is represented by a leftward pointing arrow and is entered by typing less than sign followed by hyphen. In our first example, it is used to assign name A to value 1, and once you do that, this value will be stored in your current workspace under this name, and you will be able to refer to this value by typing letter A. Later, if you assign different value to letter A, you will erase previous assignment. Also, you can use rightward arrow to assign from left to right. I won't give you any good case when you'd want to use it, but just want to let you know that it exists. What about equal sign? In many situations, it will produce similar effect, but it actually should only be used within function signatures, like you see in the third example. In this case, we created object named B of class list, which contains one element with name x. However, x in this case is not a separate object. If you would run the same command, but using leftward arrow instead of equal sign within list function, you will create two separate objects. One is list B, which contains one element x without any name, and another object x, which has value 1 and will be accessible on its own. You can read much more about the difference between those two operators on the web, and I also share some links in additional resources section of this post. Whichever operator you choose to use, make sure you use it consistently and understand what difference your choice would make. Now, as if what I just told you wasn't confusing enough, there is also a third assignment operator with double arrow. Let me explain it to you on an example. Don't be scared away if you do not understand all code, just try to follow the logic. All we do here is define a function called power, which takes as an input a numeric value, and uses this value to define an inner function, which in turn takes its input value and rises it to a power, which was defined by outer function. For instance, we can use power function to define a function called square, which will take any input and will rise it to second power. As a part of the outer function definition, we assign output of the inner function to letter I, and then we print its value. So as you see, typing square function with input 5 will print out 25. That's what we expect. However, if you try to print I outside of the function, you will get an error saying that it's not available in global environment. First, what is environment? In a nutshell, environments is just a hierarchical way for R to store objects. Whatever we store in global environment is accessible to all child environments, but things which are defined in child environments, unless called within these environments, are not accessible to parent environments. And so, because function square was defined not in global environment, but within the function power, which receives its own environment, we cannot access object I outside of the power function. To override this behavior, you can use double arrow assignment operator when defining power function, and in this way, object I will be assigned within global environment and thus will be accessible outside of the function power. I'll cover subject of environments in later series of the diary, but I hope you grasp the part which is relevant for now. Let's switch to something a bit more straightforward. Sequence operator, which in R is symbolized by colon. You can use operator to do things like generating a sequence of integer values with step 1 if you start with smaller and end with bigger value, or step -1 if you do the other way around, as you see in the second example. This relatively simple concept can save you a lot of time when you are trying to generate sequence of numbers in certain range, or you need to subset, I'll talk about subsetting later in this video, certain elements of the data structure. In these situations, you will be able to reference them by their position, which you will define with sequence of integers. So let's move on to subsetting. I don't want to disappoint you, but there is also more than one way to subset values in R. But this time, it should be more straightforward. Let's start by creating a character vector with 5 letters. Then, if you want to access elements of this vector in positions, let's say from 1 to 2, you can do that by typing the name of the object, which we call vector, and add square brackets with index of elements you'd love to subset. This syntax will also work for just one value, no matter if it's represented as single digit or a numeric vector. But there is more you can do in this way. For instance, if we have vector made up from 5 numbers, we can subset elements which meet conditions we specify by relational operators. That's example number 2 on this slide. Mind that conditions should make sense for the data which your object contains. For instance, you cannot use less than operator if your object contains character values. One use case I find especially handy is when you need to split data in training and validation sets for predictive modeling. Let's say we have our imaginary one-dimensional set with 5 values, and we would love to randomly select 60% of these values as training set and the other take as validation. This can be accomplished by generating necessary number of random values, in this case 3, and using those numbers as index to subset our data. Then, with minus sign, we can select the rest of the data as validation set. Subsetting with square brackets also works for multidimensional objects, like tables. In such situation, you should specify condition for each dimension and separate them by comma, even if you enter condition for only one dimension. For instance, we can combine 2 vectors we just created into 2-dimensional data frame, and then select only first 3 rows of this table by typing their index within square brackets followed by comma. Since rows is the first dimension, we put rows index before comma, and as we want to select all columns, we do not type anything after comma. But we certainly could do that as well. So in the last line, we select just first 3 elements of the second row, which returns a vector object because we're down to 1 dimension here. Now, let's briefly talk about the difference between single and double brackets. It's best exemplified when dealing with objects of class lists. Lists, unlike vectors and tables, can contain objects of different types and dimensions. But for our example, we have a list which contains just 2 vectors, 1 character and 1 numeric. If we access the first element of this list with index put in single brackets, what we will get in return is going to be a list, but with just 1 element, called vector. If we use double brackets, output we'll get is going to be the vector of characters itself. That difference becomes important if you want to take subset of the element inside the list. For instance, in the second block of code, you see that output is null value because output of the comment list with index 1 with single bracket has only 1 element. And trying to extract second element from this output won't give us anything. Whereas, if we use double brackets as the first index, our output will be vector with 5 values, and we should be able to extract second value from this vector by typing second set of brackets. Also remember that you cannot use column to subset sequence of elements when using double brackets. Finally, there is also a third way to subset elements which have names attached by using $ symbol. For instance, we can access second element of the list we've just created by using name of the list followed by $, followed by the name of the element in this list. One benefit of using $ symbol instead of square brackets is that $ symbol works with partial match. For instance, typing list $n will also return vector of numbers, since this is the only element in the list which starts from this letter. Using partial match is not encouraged, however, since this can create confusion for you when trying to understand your own code, let alone for other people. If you want to access element by their name using square brackets, you should put name in quotation marks, and if you would like to use partial matching, also set additional parameter exact to false, since it's set to true by default. On the other hand, subsetting with square brackets works with computed values, as you see in the third example, but this won't work for you when using dollar symbol. Parentheses and braces. Each of them have distinct application in R. Parentheses are used in R for the same reason as when you write simple math expressions, to determine the order of conducted operations. So I hope you will not have any trouble understanding why the result of the first expression is 7, whereas the result of the second expression is 10. Braces, or curly brackets, allow to evaluate several expressions in one row, and return only the result of the last expression if it implies any output. Expressions in braces should be separated by semicolon. That's quite handy when you're trying to make your code compact, so you will see me using it more in the next few slides. Next, we'll talk about a number of operators, which most of you would know pretty well if you ever used calculator in your life. But I hope you'll understand that R can become your most powerful calculator once you learn a few simple things. So, in the first example, you see application of arithmetic operators to numbers. And as you just learned, you can apply parentheses to define the order of operations. Apart from numbers, you can use logical values to perform arithmetics. In such scenarios, R will treat true as 1 and false as 0. This is very useful when you want to summarize a logical vector by calculating number or percent of true responses. Also, arithmetic operators can be used with computed values, if these values evaluate to numbers or logical values. You cannot, however, apply operators to character strings. There are other special commands in R which you can learn to do that. Previous example probably didn't impress you much. But R is really powerful when dealing with more complex data structures. For instance, you can take a vector of numbers and multiply each element of the vector by some other number and then add third number to each of the results. And all of that is just one line of code. It's also possible to work with two data structures at the same time. For instance, you can cross-multiply each element of the two numeric vectors, even if the vectors are non-conformable. You still will see the result, but you will also get a warning, which in this case means that the sixth element of vector 3 had nothing to be multiplied in vector 2, so we just see the original value. Finally, sometimes you may need to calculate the remainder of the division of the two numbers, which is called modulo. This is often used when trying to implement iterative procedures. In R, modulo operation is performed by typing two % signs without any space between them. So in this example, you see that dividing 128 by 14 will leave us with the remainder of 2. You can check yourself easily. And the last note is about matrix multiplication. If you have two numeric matrices of conformable dimensions, you can perform element-wise operation on them using symbols we just described. If, however, you would love to perform true matrix multiplication, you need to use the special symbol which is produced by putting a multiplication sign between two % signs. That's of course not everything you can do with matrices in R, but that topic requires special attention and doesn't fit the scope of today's video well. Another important set of symbols which will make R more powerful in your hands is relational operators. These symbols allow you to ask if certain value is larger, smaller, or equal to another value. But as everything else, there are some small caveats to know about. So let's start from the first example, where we ask if 3 is smaller than or equal to 2. Note that we put equal sign after smaller, not the other way around. And the same way for larger than or equal. And the output we get is false, which is logical value that also evaluates to 0 when we apply arithmetics to it. As with the most of the things in R, relational operators can be applied to arithmetics, that's example 2, and computed values, that's example 3. Operators which are pretty not standard for non-programmers here are equals to and not equals to. The equals to is denoted by double equality sign, and its opposite is denoted by exclamation sign followed by single equality. And of course you can apply these operators to data structures such as vectors and matrices, providing they have identical dimensions. Note that we would not be able to compare a vector with 5 elements to the one with 6, as we could do when applying arithmetic operators. Also, when comparing an object to itself, we are getting just one output value, whereas if we are comparing two identical objects, we'll get as an output element-wise comparison. And finally, comparing an A value to another NA or an AN value will always result in an A, no matter what. If you're still bearing with me, congratulations! This is our last piece of heavy theory to lift, so I hope you're ready to use some logic and learn how to implement it in R. Specifically, how to combine multiple conditions created with relational operators, so that you can test for more complex scenarios. Let's have a look at the top example. We have a vector of 5 integers, from 1 to 5, and we would love to know if each of the elements in this vector is larger than 1 and also larger than 5. We can combine these conditions using ampersand symbol, and only one in this case. The answer we get is that none of the symbols meet both conditions. Using double ampersand sign, we'll evaluate just the first element in our vector against both conditions, and we'll return the result as a single logical value. I am yet to discover some useful applications for this specific operator, but I'm sure it has some, so now you know the difference. OR operator is denoted by vertical line, and the same rules apply to it. Single line will evaluate each element, double only the first one. Do not confuse double operators with double conditions, which you can implement with both and OR operators. You can also check for more than 3 conditions at the same time, but you probably won't do that very often. In addition, whereas technically it's not non-alphanumeric operator, I still wanted to pay your attention to XOR function, which allows to check if any of the conditions you specify within the function are met. If yes, you'll get true, and false otherwise. And the last nut to crack is the logical operator, which stands for not. Not should not be confused with not equals to, which is denoted by exclamation sign followed by equality. The not operator is denoted by exclamation sign only, and can be used only when applied to logical values, like in this example. Let's go over it line by line to understand what's going on. Imagine we have a list, which contains 2 elements. One is a vector of letters, and the second is a vector of numbers. The first comment just prints out names of each element in this object. Then we go ahead and assign one of the names of the elements in the list to value x. Then we use match operator to check if x value is present in any of the names of the list. Match here is implemented by using in command put between 2% signs. That's not something you should know about, but just in case you are curious. As an output, we get 2 logical values, which tell for each element in the list if its name matches to x. And it does for the first element, since we assign the same value to x. Finally, we use not operator to subset the list by selecting elements whose name does not match the value of x. So you can read the last comment as find if x is matching names of each element in the list, and return only the elements which do not return value true when matched against x. And hence, since element letters does return true when matched to x, we see only numbers element printed out. Woohoo! Now, let's take a few minutes to cool off, and I'll talk about 2 quick and easy things which will end our overview of our operator syntax. The first is question mark, which you can use to search for help documentation right from within R console. Often you can achieve the same by using Google, but in many cases it's more convenient to do it right directly from interpreter. To search for a specific document, enter its name right after question mark. For instance, typing NA after question mark will pull up documentation page about missing values. Some objects, including all of the ones which we talked about, also require quotations when searching for them with question mark. Note that when using one question mark, you should know in advance what exactly is the page you're looking for, and in most cases you will use names of functions, packages, and operators to do this kind of search. If you're not exactly sure what specific document you would like to see, you can use double question mark to search for all documents which match your search string. That's more like searching on Google. Also, if you'd like to limit your search to a specific package, providing that you know what package you need, you can add it to search query by using pattern shown in the last line. And the last operator for today is tilde, which is used within functions when evaluating particular statistical models, like linear regression model. Tilde is used to specify formula for the model you want to evaluate and separate left and right sides of the equation. That's the only operator which I have not found the key to print on Mac, so I always do Google search for it or copy from my previous code. If you've reached this point, congrats! You've completed quite comprehensive overview of our operator syntax. We'll skip summary section in this video, since that would essentially mean going over each slide again. Instead, I'll encourage you to visit my tutorial page, download cheat sheet which you can use for regular revision. There's also a code file which you can use to practice on your own. And finally, there's a ton of very useful additional resources, which you should now be able to understand. Being familiar with them and knowing where to look for things when you need them will make you much more independent and professional R user. Best of luck and stay tuned for the next episodes in this diary.